Alright, sorry for this. Let's begin again. So, sorry for this again. As I've said, the topics we're going to be covering today are neural networks, computer vision, and natural language processing. So, the first thing that we're going to be doing is neural networks. Alright, so you might have seen this complicated diagram. I'm visible, right? Yeah, it's visible. Okay, let's go. So you might have seen these complicated diagrams of a bunch of circles and a bunch of lines, weights and biases. So what do they actually mean? Now I want you to think of a neural network as a function finder and just ditch this complicated diagram for now. We'll come to it later. Function finder, that's what I want you to keep in your mind. Alright, what does a neural network even do? So it fits curve to data. Now what do I mean by this? Let me give you a simple problem, right? Say we have 15 people and I have given you the height and weight of these people in the graph on the left side. Okay, now I ask you a question. For a new height, say 3.5 meters, what do you think the weight would be using this data? Something around here, right? Now I ask you what the height would be for 2.5 meters, somewhere over here, and then again you will say something here. So what we need to solve this problem is actually a function which is derived from this data, right? We need a function which is derived from this data to make predictions about new data. So this is what is the major challenge in real life. Even in stock markets, looking at the past trends, we try to make a new prediction. So as you can see, neural networks are of great importance, and what neural networks do exactly is they find this function, right? If you can see these data points, the job of a neural network is to find a function which accurately represents this data. Alright, let's continue. So as you can see, I have drawn two curves here. One is the curve on the left side and the other on the right side. Now I would ask you which curve accurately represents the data. Now it is obvious to see that the curve on the left is going to be much better than the curve on the right because it is less noisy and it's smooth, like you get it, that this accurately represents the data. So our goal of a neural network is to create a curve, but now this curve should be smooth. I mean, it should not be very noisy, like up and down, like spikes and all. So that should be the approximate goal of a neural network, to find this function. Now let's see how a neural network actually finds this function. Alright, say we have our data is something like this. Alright, these are our data points, and we wish to find a curve which looks something like this. Right, not exactly this, or it should look like this approximately. A little bit up and down is fine, but the curve should look like this. Now in your 11th and 12th, or maybe even in your first year, you might have come across a chapter of waves and oscillations, in which what we do is we take multiple waves, or for example standing waves. What we do is two waves interfere and they create a new shape. So similarly, what the intuition behind neural networks is, we use many simple functions and we join them together in certain way. I mean, we squish them, enlarge them, and we join them to get a complicated looking shape. And there is a universal approximation theorem for neural networks which states that if the neural networks is dense, then we can represent any type of complicated graph. In simple words, what this is trying to say is, if we have say 1,000 simple functions, then using these 1,000 simple functions, we can join them in a certain manner and create any type of complicated shape. Now, is this 1,000 or a million or 10 million smaller functions? That depends on how complicated the graph is. If I have something like a simple parabola, then I might need only one simple function. But if it has many wiggles, then I might need hundreds of simple functions. Now, what are these simple functions, and then how do I squish them? How do I enlarge them? This is what the task of a neural network is. Let's look at a Desmos visualization here. Alright, so as you can see, these are our data points over here, and the curve we wish to find is something of this sort. We wish to find a curve which represents this data. Alright, now firstly I would like to introduce a term of an activation function here. Now activation function is simply for now a non-linear function. Alright, so we'll be taking the standard function here, which is known as the sigmoid function. As you can see, this is a sigmoid function. Nothing pretty complicated, it's just a normal function. Alright, now I'll show you three simple graphs. One is sigma of phi times of x, another is sigma of phi times of x minus 10, and the third one is sigma of phi x minus 30. Let's look at this graph. Phi x, nothing complicated, the graph just increases in height, as you can see over here. And another graph, phi x minus 10, it just shifts a bit. and another graph it shifts by this, right? Just simple graphs. There's nothing complicated in these graphs. Now let's look at a linear combination of these three graphs. This is the key point. When you look at a linear combination of these three graphs, voila, you get the exact curve, right? This is the main intuition. We use simpler functions and we try to get a complicated shape. Now you might ask, how did I get sigma of 5x? How did I get sigma of 5x minus 10? Where did I get these numbers 3, 6, 3, and what is the method of joining? See, I can't choose any random way and tell that, okay, you just join these two and you get this good looking curve. So what I need is like a proper rigorous manner in which I have a way to construct the simple functions and I have a way to join the simple functions together to get a complicated looking curve. Like as you can see, now it might just seem like magic that I got 5 times of x minus 2, 5 times of x minus 6, 3, 6, 3, and I got the complicated curve. But what the neural network does is it constructs these values for you. Right, let me elaborate how it constructs these values. So initially, before having this 5x, 5x minus 2, 5 times of x minus 6, we create a template, right? We make an assumption that our complicated looking graph can be thought of as a construction of three different simple functions. As you can see, we assume that the first simple function is sigma times of a linear function w1x plus b. Now here I would like to introduce a terminology which is the weights and biases. As you can see, the numbers w1, w2, w3 and w4, w5, w6 are known as the weights, and the values b1, b2, b3, b4 are known as the biases. Initially, these values are going to be randomized, right? We don't know what these values are. Our goal is to find these values so that the curve transforms into the second curve over here. Let's look at another Desmos visualization of what I'm trying to say here. Okay. So as I told you, we create a template. This template is, as you can see here, these calculations can be represented as this computational graph, which saves us a lot of space. That, as you can see, x, w1, b1. So h1 is w1x plus b1, h2 is w2x plus b2, h3 is w3x plus b3. Right, so this is a computational graph and this is how you represent it, and y is a linear combination of these three. Now you might ask me that why did I make such an assumption, that why do you think that this complicated figure can be represented as a linear combination of these three? Like as I told you, there's a theorem called the universal approximation theorem, which states that if our that we can represent any complicated curve as a combination of simpler curves. Now as you can see, this curve is pretty simple. Like, I mean, there are very complicated curves as well, but for this curve here, with trial and error, you can figure out that only 3 neurons are sufficient. I mean, if the curve is very, very complicated, then you might need 10 neurons, that is 10 equations over here, right? Because this curve is simple, we use only 3 equations here. Now, as I said, these values are going to be random at the start. This is the key idea here. As you can see, I'm going to initialize these two random values and let's just see what kind of a graph we get, right? As you can see, the graph that we get initially is pretty random and it does not represent the data at all. Now what our goal is to change these values and change these weights and biases so that this graph over here transforms into this graph over here. So our goal is to find the weights and biases so that the graph on the right transforms into the graph on the left. Now this is what a neural network does. It finds the values of these weights and biases so that the graph transforms into this. That means the graph becomes more accurate to the training data that we have. Now see, I can't just by looking at it, oh, the graph is pretty down, let me increase it up. Okay, I increased it up. Now this weight, let me reduce a bit too. See, I can't do this manually and figure out that what the changes to be made so that the graph becomes better. I need a systematic way of, you know, converting the graph, that how much should I change the value of W4, how much should I change the value of B3 so that the graph that we get is, you know, tending to be closer. Now this systematic way of changing the weights and biases is known as backpropagation and gradient descent. Now this involves a bit of heavy maths calculus, which you guys will be learning in your first semester, that is in the multivariable calculus course. and I would skip this part for now, and I would just teach you gradient descent for now, right? What I want you to take away from this is we assume that the function that we get is a combination of multiple functions, and we tweak these values so that it closely represents the function that we want. This is what I want you to remember for now. We'll deal with back propagation another time, but for now I'll teach you gradient descent. Alright, say you have a complicated function. As you can see here, just follow my lead, don't forget, get distracted in any of these diagrams, and I ask you a question: how do you find the minima of this? Now you might say, I'll just do dy by dx equal to 0, and the second derivative test, d square y by dx square greater than 0, and boom, you get the local minima. Sounds fair enough. But what if you have a complicated function whom either you can't differentiate it, or when you differentiate it you can't find the roots? So on differentiating and you equate it to 0, what if you get something like sin x equals x square? Now you can't solve this. This is transcendental equation, I believe what you call it. So what you do is you either put it in a calculator, which is like Wolfram or MATLAB, and then you calculate it. But that is not a good method, right? And that is a good method if you have Wolfram, but if you don't have access to it, then you'll have to look for another method, right, to find the local minima. So what people came up with is a method known as gradient descent. See, let me tell you what gradient descent actually does. Your goal is to find the local minima. All right. So what you do is you take a random point, say any random point A, okay, and you calculate the slope at A. If the slope is negative, then it is hinting that you have to move in the forward direction to reach the local minima. That is what your next step should be, is x nu is going to be forward, right? You move forward. Similarly, if your slope is positive at C point, to reach the local minima, you're supposed to move left, right? That's what the intuition is. Or if you look at a point B where the slope is positive, to reach the local minima, you move left. And at a point C where your derivative is negative, you move forward. Now if you look at this equation, x nu equals x old minus neta times dy by dx. Now neta is a constant which is usually a small number, something around 0.1 or 0.001, which indicates the step size. Now what essentially we're doing is we're starting at a point A, right? And if the slope is negative, we move in the forward direction. So if you look at it, x nu will become xa plus a number. So we're going to be moving in this direction, and then we come down, and then slowly as we come down, we converge to the local minima. So this is the idea of gradient descent. Basically, you start at any random point and then you take small steps, and then you reach the local minima. So this is what we're trying to do here. Now you might ask, what if I want to end up at the global minima? So what we try to do here is we take about 50 random points and then we run the gradient descent algorithm. The gradient descent algorithm is this itself. We run it about say 1,000 times or 2,000 times, and then we converge to a minimum point, and then we compare what all the minimum points we get. That is, we compare this minimum to this minimum to this minimum, and whatever the minimum we get out of all these local minimums will be the global minimum. Now this is kind of a not a rigorous way. I mean, there are other rigorous way, but you get the intuition, right? The other rigorous way involves more mathematics, which we'll leave for now, but you get the intuition. You take a random point and then you take small steps and you reach the local minima. So gradient descent is a method in which we find the local minima. Alright, let's continue. Back propagation some other time, which is how the weights are changed. Alright, now as you guys have seen the computational graph here, that x, w1, b1. So h1 is w1x plus b1, h2 is w2x plus b2, h3 is w3x plus b3, and so that's how y is also computed. Y is w4 h1 plus b4, and like that. You get the intuition. Now what do the inputs represent? They represent the function that the number of variables the input function has. Now if you study multivariable calculus in your sem 1, you'll notice that from JE in JE we had only f of x. That means there was only one variable, but in reality there can be many variables, right? There can be a function which takes two inputs, x and y. Now how hungry I am depends on when I ate my food and how fast my digestive power is, right? So if I eat more food but my digestive power is more, then I might feel hungry in 1 hour, right? So the time taken to feel hungry is a function of two things: how much food you ate and how much is your digestive power. So to predict any type of function, right, that is any 2 variable function or 3 variable function or even n variable function, so you have 100 variables, you have something which depends on 100 independent quantities, you can still use the same architecture and run the backpropagation algorithm to find the function. See, this is the thing that we are taking away from here. Now, even if you guys didn't understand anything from here, this is what I guys want you to know. A neural network is a model, a mathematical model or a machine which takes in input the training data and gives us an output the weights and biases. Now, what are the weights and biases? If you look here, these values 5, 2, 5, 6, 3, 6, this is what the neural network figures out through learning. Alright, and why is this needed? Because we need to join them to create a function. And the term learning means adjusting the weights and biases until the prediction matches the training data. Now, if you guys remember, the weights and biases that we started were initially random, and the graph that we got initially was completely random. Now, our goal was to adjust these values of weights and biases so that on transforming, this graph eventually becomes this graph. So if you look at the values, W1 was 5, I believe, so I'll just make this 5, B1 was 0, and see, if I make all the changes, W2 was again 5, B2 was minus 10, W3 was 5, and B3 was minus 30. And if you see, the graph is somewhat closely representing the data as I make appropriate changes. This was 3, this was minus 6, this was 3 again, and this was 0. Now, as you can see, the graph closely represents. Now, what initially started with a random curve, somehow we changed the weights and biases so that it matches the data. This is the exact function of a neural network. It finds what changes are to be done. Alright. And if you have heard of CNNs, RNNs, transformers, have you guys heard of ChatGPT? Obviously, you have heard. Now, what is the full form of GPT? Generative Pre-trained Transformer. The T in ChatGPT stands for transformer, and that is also a neural network. And see, ChatGPT takes an input, your words, whatever you have entered, and gives an output. That is also a function, as you can see, and functions equals neural network. You have to find the function. So that's what, that's what everything actually really is. Everything is neural networks, but the architecture will obviously be slightly more complicated, or should I say, it'll be very more complicated than the architecture of the simple neural network, because it's very complicated. Alright, let's look at some examples. Alright. So you guys have seen the sin x curve, obviously, and let's see how a neural network learns the sin x curve, right? Actually, there's another term called training, which I've done beforehand. If you guys want to see how I reduce the loss, and we'll come to that later. Alright. The red curve that you see here is actually the prediction of the neural network before training, right? And as you can see, as the epochs go ahead, and now epoch is a new term. Epoch means one training cycle, right? So after 360 training cycles, as you can see, the graph is slowly coming closer to the blue graph. Now the blue graph is sin x, and the red graph is what our model is predicting. Right, so as you can see, training is a time-taking process. My laptop is Ultra 9 or something. It has 8 cores, and yet it takes so much time now. And this has only very few parameters. I think about 100 or 200 parameters. Now ChatGPT, Claude, they have trillions of the parameters, and you can see compute is something which is very expensive, and it takes time. That's the point here. And as you can see, as the epochs are going ahead, the red curve is slowly trying to come closer to the blue curve. Now if I increase my training data, here I have taken only minus 3 pi to 3 pi, I believe. Now if I increase the training data to minus infinite, say minus 30 pi to 30 pi, and increase the compute power, then I can predict any shape, right? That is the takeaway from here. Alright, cool. So as you can see, what started with a random figure now closely represents sin x. Alright. As you can see here, the function which initially started as completely a random graph The red one is the before training one, and after your epochs, it closely represents, after training, it represents your sin x graph. So that is one example of what neural network does. It takes an input as your training data and it tries to learn the functions like a robot, tries to mimic what it does, right? Basically rat try. It's buttifying, if you have heard the term in organic chemistry. That's what something of a sort what a neural network does, right? That's it. You just have to learn the basics of this, and let's go. Let's look at computer vision now, or should I say the introduction to computer vision now. In this section, we'll be looking at convolution, spooling, convolutional neural networks, and the application of artificial neural networks. So let's begin. Now, let me give you a very trivial problem of what you can think. If I give you an input image like this, I want to give it to a program so that it gives an output 3. Now this might seem very trivial to you because this is obviously a 3. I mean, there's no confusion at all and it looks very trivial. But how do you want to write a program which takes in this input 3 image and gives an output 3? Like if you give it to ChatGPT, this image of a 3, it's going to instantly tell you that it is a 3, right? But it seems very trivial, but the problem is it is not that trivial, right? How do computers see this? Like if I give an image of a cat, how does the computer know that it is a cat? This is the main challenge that we are dealing with computer vision. Like if your car is going to collide, how does the system know that there is something beside it, right? So that's what it is. Alright, let's continue. So to input this image 3 into a program, firstly we'll have to convert this photo into numbers, right? Because your computer or your program, your Python code, C++ code or C code, it does not understand pictures, it understands only numbers. To be specific, it understands binary, but then you use compilers to convert it to binary. But the thing is, if you give an input, I can't input this picture as it is to the program. I need to give numbers, right? So how do you want to convert this picture, this 3 here, into numbers? One idea would be to, what you do is based on how illuminated they are, you can assign the black pixels to 0 and you can assign the white pixels to 100 and the gray pixels to 50 or 60 based on whatever, how illuminated they are. If you look at this brightest pixel, you can give this as 100 and the blackest pixels you can give it as 0. Or another method what you can do is you can give the black pixels minus 100, the white pixels 100 and the gray pixel somewhere around the center is 0. That is one way you can represent your picture as numbers. Alright. Now to solve this problem, like, do you get an intuition that if I write 3 and you write 3 and you take a zoomed in picture, these two pictures would have similar values, right? Not at all places, but at most of the places they might be similar. And your program, what it essentially does is it takes a few numbers and gives an output. Now this is the function, this type of a function, and you want to build such a function, so neural network is born, right? This is where the notion of a neural network comes into picture. Right? Even if you didn't understand anything from the past topic, which is the neural networks, what I want you guys to remember is a neural network is a machine or a black box, you can take it, which you don't understand, which creates functions based on the data that you give. So if I give few data points like this, it just fits the curve like that. That's it. It's just a function fitter. Moving on. Right. Now as you can see, I want to convert this picture into numbers. We taught the AI how to read, but what if we want to teach it how to see? Like as I mentioned, to a computer, a picture isn't a picture. It can't understand a picture. How do you give a picture to a Python code? You need to convert it to numbers. So this is what you do. If an image is black and white, pure white, you can give it the number 255 or 1000 or 100, any number which you want. Pure black can be 0 and gray can be somewhere in the between. So every pixel can be represented by a single number in a black and white image. Alright. Now here's another issue. If you look at this image, this is a 2D grid. Right? This is not a single line or a layer of numbers. It is 2D. So how do you want to give this to a neural network? If you remember previously, what I told you, how do you give inputs to a neural network? It has to be a single layer, right? X, Y, and then if perhaps more inputs, Z, W, and so on over here, right? Now, this is a 2D grid. How do you represent a 2D grid to a neural network? So one way what you can do is you can flatten the 2D grid. So you can take the first layer, the first row, and you can place the second row beside it and the third row beside it, and the entire line you can give it to a neural network. This might be a bit difficult to understand, so I have an animation of this from 3 Blue 1 Brown itself to open on YouTube. Yeah, as you can see here, let's look at this animation where he takes the same example which I told you. This is a very famous example of image recognition. This is like the first go-to example. This is the holy bible of the image classification. So if you have this grid of numbers, like as you can see here, he chooses white as 1 and black as 0. Now how do you want to give this to a neural network? Look at this, look what he does. He breaks them apart and then he puts all of them into a single line, 784 pixels that you get it, and then you give this to a neural network. Let's look at it again for increasing the clarity. You split it, you bring it to a line, and you pass this into a neural network, right? So essentially the neural network then is going to learn the function. So the output 3 that you get here can be expected as a function of the input that you give, right? So that's what a neural network does. Based on this, it finds the function of how the values of the pixels are related to the output, and then we're done. All right, let's look at an implementation of a neural network which detects handwritten digits. All right, now I would like to bring a term MNIST. What is MNIST? MNIST is a data set basically which contains 60,000 images, handwritten digits, right? So many people have contributed to this. They write 3, 4, 5, 6, and they have corresponding labels, and we can use it to train our neural network. So training takes time, as I mentioned, the epochs, as you have seen it. So I had trained the neural network before itself, and what we do, one more thing here is, see, we have 60,000 training images. Now we break this set into 2 parts. One is going to be your 50,000 images for training, and the 10,000 images are going to be for testing. Now I'll tell what the use of this testing is in a while, but as you can see, we get an accuracy of 97.4% here. That means for out of the 60,000 images, 97% is, you get 97% of the images right after this. So as you can see, I've already trained the model. Let's just see a demo of correct pictures first. All right. Yeah, this is one of the image, like 8, and the model classifies that this is 8 with a accuracy with a percentage of 100. There's no doubt that the model thinks that this is 8. Let's look at another example. Yeah, for this 6, the model thinks that the image is 6 with 100% accuracy. Now one more thing I forgot to mention here is, what do you think the output of the last layer should be, right? Because in y equal to f of x, if the input is the values of the pixels, what do you think should be the output? Should it be the numerical value 3, 4, 5, 6, 7, or what do you think the output is going to be, right? So the better way of representing the output is going to be a probability distribution of what the model thinks the number is. So if the pixel 8 gets a value 1, that means the model thinks this picture is 8. So a correct model would give 9 a score of 1. 0.5 is a bad score, 0.38 is a bad score. If it gives 0.97, that means the model thinks that 9, the picture's value is 9. So this is the last layer, and yeah, let's look at the examples. Yeah, 6, and now see, I've mentioned 97% accuracy, right? There are some pictures which the neural network isn't able to classify properly. Let's look at such images, right? All right, this is one of the image. This is, what do you guys think this is? This is a 4 or a 9? I mean, it's pretty close, right? The answer should be 4, but the model thinks that it is 9. I mean, you can cut it some slack because this is very, it's an ambiguous photo. Right, let's look at some more examples. If you look at this, what do you think this is? The model thinks that this is a 3 and not a 5. And this is also pretty ambiguous because if you add the top left arc, you get a 3, and if you add the line there, you get a 5. So this picture is also slightly ambiguous, and this is where the model fails. So 97% accuracy feels good, but can it be better? Can we get 100% accuracy? Can we get 99% accuracy is what we are always hoping for. So let's proceed. Alright, so summary of what we have learned till now. A neural network is basically a function finder, as I've told a number of times till now. And the intuition here is your output is a function of your input that you give, obviously. And the neural network just finds this function through its back propagation and gradient descent, which is it's a math heavy thing, but just understand this for now. Alright, let's continue. There are issues with traditional neural networks. First thing is going to be there are too many parameters. Now, what do you mean by parameters? Parameters are nothing but weights and biases. If you looked at the first thing that I've shown here, this diagram, how many parameters do you think this has? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This has 10 parameters. Now, for training this Sin-X graph, I have used about I think I've used 5,000 parameters just to train Sin-X. Right, just for training Sin-X I've used 5,000 parameters. That is two hidden layers of each 12 and the connections, you can count it, but you get an idea. So traditional neural networks have a lot of parameters, which is we need more compute power. This is not a good thing, right? Because compute is expensive, it's obvious. And then another issue is that I've told you, right, you take the grid and then you compress it into a line. At each row you append it after each line, and then you just feed it into a neural network. I mean, this might seem good enough, but we are losing the geometry here, right? Which pixel is next to each other has no significance at all while deciding what the image is. So it has no spatial significance, which is an issue here. And yeah, so the newer models that we get try to fix this issue, and let's see how they fix it. So people have invented something called convolutional neural networks, which is a breakthrough in terms of computer vision. But what exactly are convolutions? What even is a convolution, right? You guys must have obviously heard of addition, subtraction, multiplication. Similarly, convolution is just an operation. To give a better example, if you guys have heard about dot product, how you take dot product or cross product of two vectors, convolution is also something which is an operation on two vectors or two matrices or anything like that. So let's see what convolutions are in a second. I'll have some water. Give me a second, guys. Oh no, the video isn't playing. Can't see anything. Alright. Couldn't see the video. Where are my maps? It's not visible. Give me a second. Yeah, I guess it's visible right now. So Yeah, as I mentioned, sorry for that again. So I'll just begin with. Yeah, so the video is visible. All right, cool. All right, so yeah, as I was saying, you want to give this matrix of numbers into the machine. So you basically do this, split it, and then you pick it into line, and then you put it into the network. Let's just see that again. You have your numbers. As you can see, 3 blue 1 brown is a good animation channel. He teaches math very nicely, so you can look into the channel for further videos as well. As I mentioned, I chose 100 and 255 as the max limit, but he chooses 1, so you can represent the whitest pixel as 1 and the blackest pixel as 0. And yeah, that's what he does here. He stretches them out and then concatenate them, basically. As you can see, he just joins them, and then you put that into a neural network, and then the neural network, through its magic, backpropagation and gradient descent, it learns these values, and you make a good prediction out of this, right? There's one more thing I wanted to address here, that what do you think the last layer would be? The last layer, rather than it being a single neuron where it shows the value, it would be much better for the neural network. I'll discuss that in some time. I'll discuss that in some time. That 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, what these are the probabilities that the machine thinks this model is. Now don't get confused by probabilities. It's just a function, it's just a number, right? So if the model thinks that the value is 0.5, that is bad, right? Because 9, I mean, this is clearly a 9. If the model thinks that the output for 9 is 0.5, it is bad, and 0.38 is even worse. But if the model outputs 0.97 for 9 and close to 0 for all the other values, that's pretty good. Yeah, that's awesome, right? Because you're getting an accurate prediction. So this is what is the idea of convolution neural networks, and let's proceed. All right. No, this is the idea of artificial neural networks. I got distracted for a second. Alright, let's continue. So I've told you the issues with traditional neural networks as well. Too much compute power and etc. Pixels are close to each other, will use geometry, and let's continue. What are convolutions? Like, as I told you, they're just convolution is an operation of two vectors or two matrices. Let's see what actually that means. Alright, this is what you do. Suppose you have two vectors here. One is a1, a2, another is b1, b2. If you guys don't know what vectors are, just consider as two numbers in a list. So how do you compute a convolution? So the convolution between a and b, which is denoted by a star b, is this: a1 b1, comma a1 b2 plus a2 b1, comma a2 b2. Now how is this calculated? You flip this b1 b2, and then you compute this product a1 b1, then you compute a1 b2 and a2 b1, then you move the sliding window. So these two were the windows like this, and then you move this window here, and then you move this window here, and then you compute the elements, as you can see here: a1 b1, then you move it, a1 b2 a2 b1, then you move it another side, and then you calculate a2 b2. This is defined as the convolution operation. And for if you have three-dimension vectors, first you compute a1 b1, and then you compute a1 b2 plus a2 b1, and then you move it. You get three terms, then you get two terms, then you get one term, and then that's it. So this is how 1D convolution is done. Let's just look at another animation which we have. Oh my god, what I have ads? What's the timestamp? 6:27. Alright. Alright. 6:27. Alright. What is 1, 2, 3 convoluted with 4, 5, 6? Let's look at it. You switch this side, you move it this side, and then you compute it element wise. Compute 1 times 4 is the first element, then you move this side, and you compute 1 into 5 and 2 into 4, and you add them. Just have a look at it. Then you move it again, and then you And then yeah, so this is how a convolution is computed. And yeah, that's how 1D convolution is completed. And what do we guys know till now? That convolution is just another operation, which is like a dot product or cross product or something like that, which is that has certain rules and how it is computed, sliding window method. And I'll tell you what the use of this convolution is and how it improves your neural network. Right. So coming to 2D, let's look at another animation here of how a 2D convolution is computed. Right. So how a 2D convolution is computed is, so right, the thing that is getting convoluted on is called the input, and something which convolutes the input is known as kernel. As you can see here, the kernel and the input. Right. So how do you compute these two convolutions? There's a set of rules. Okay. Now, what this happens is, to compute the first element, you put this kernel on top of the first overlapping brick. He'll do that in a second, just watch it. Yeah, he does this, and then he computes the element wise product sum. So as you can see here, the numbers 1 2 1 0 0 0 minus 1 minus 2 minus 1 come here, as you can see, and the numbers from this 20 19 21 come over here, and you compute the sum. Right, hope you guys understand it. You just put it over there, and then you compute the element wise sum, and then you add it, and there's going to be your first element. The sum that we get is 3, and then you put 3 over here. Now what you do, you slide this window over here by 1 unit, and then you compute the sum again. This is going to be 27, and then you repeat the process. That is, first here, then here, then here, then here. So you do it 4 times over here, and then you move it 4 times down. So essentially you get a 4 by 4 matrix, as you guys can see over here. This is the thing. Just have a look at it one more time so that you cement your understanding. So he has the kernel and the input slice. Then you, now this type of kernel is called a Sobel kernel. I'll talk about it in a while. So you put it on the first element, and you compute element wise product, and then you sum all of them up. So it's just 20 times 1. See, 20 times 1, 24 times 0, 11 times minus 1, 19 times 2, 17 times 0, and you sum them up. So this is how a 2D convolution is calculated, and in a while I'll explain what the need of this is. Right. So 3 and stride of 1. So you move it by 1 unit, and then you compute another sum, and then you put it there. So this is the output of the convolution operator. Cool. That's nice. Alright. Now, yeah, what is a convolution operator? It uses a tiny window, usually 3 by 3 pixels. It slides across the image looking for a specific pattern. We call this window of a filter or a kernel. Yeah. Now there's another, I'll come to the what is the use of a convolution in a while. Yeah. Let's actually look at this convolution part itself. So now I have two filters known as the Sobel filters, right? One is Sobel X and Sobel Y. Now these are just mathematical numbers. I mean, when you put -1, -2, -1, +1, +2, +1 and zeros, this is known as the Sobel X filter. This matrix is known as the Sobel X filter. Now, what do you think will happen when this filter slides across this image? Right, let's have a closer look at this image. Now, see, this is the notation that I'm trying to use here, is that 100 is going to be white, 0 is going to be gray, -100 is going to be black. As I told you in the starting, do you remember that based on how much it's illuminated, I'm going to give it a number. So 100 is white, 0 is gray, -100 is black. So let's alright, there's one more thing I want to clarify. This image is huge. It has about 1,000 pixels, right? It's just shrunk in size, but it has 1,000 pixels, and this is only a 3 by 3 matrix. So this is a 1,000 by 1,000 matrix. As you see here, this is a 6 by 6 matrix, right? This image here is actually a 1,000 by 1,000 matrix, and the kernel here is 3 by 3, and here also it's 3 by 3. The scale doesn't do justice to the diagram, but stay with me here, right? This is a 1,000 by 1,000 matrix. All right, let's slide this image. Let's actually forget about Sobel Y for a while and just look at what happens when you slide it across, right? So if you look at the top part where it is completely black, what happens when you put this matrix over it? Now all the black pixels are equal. Do you guys agree that they have a value of -100? Now what is going to be the output when I put this 1 times minus 100 plus 2 times minus 100 plus 1 times minus 100, which is going to be minus 400. And then when I apply the left side operation, that is going to be plus 400. So you get 0, right? So wherever there is black in the image, I'm going to get 0. The value is going to be 0, which is gray. And wherever it is white, right, I mean it is uniform throughout, right? When I apply this convolution, it is basically doing right minus left, like approximately it is doing the value of right pixels minus the left pixels. And if right pixels are equal to the left pixels, you get it as 0, and 0 is gray. So the black part is gray and the middle part is also gray, right? Cool. But what do you get on the edges, right? What did I tell you? This does basically right minus left, right? Because right is plus and left is minus. Now the right on the edges wala thing is fully positive because it's going to be plus 400, and the left side is going to be minus 400, and you add this, it's like 400 minus 400. So this edge is going to be fully illuminated. It's going to become white, and this edge should become black. Let's see what happens in this. Is there a picture I've added? Yeah, as you can see over here, when you apply the Sobel X filter, everything of the image becomes gray other than the edges. This is going to become white and this is going to become black, because right minus left, right, black minus white is going to be minus 400 minus 400. So it's going to be even blacker, and the rest of the image is going to be gray. So what we essentially did here is, given an image, we were able to detect vertical edges, right? Do you guys understand this part? We, given an image, we are able to detect vertical edges. And you might ask what happened to the top edges. The top images, right minus left is going to be the same, so they're going to become gray in the end. Now if you look at the Sobel filter, y direction, it is plus in the top and minus in the bottom, so it's going to be top minus bottom. So you would expect the top edge to be black and the bottom edge, top edge to be white and the bottom edge to be black, because white, wait, what? I think there's an issue here. Okay, there's a slight correction in this image. It is top minus bottom, so this is supposed to be black and this is supposed to be white. It's top minus bottom. Just ignore this for now. It's an issue with the diagram. The top, yeah, you get it. It's top minus bottom and right minus left. Now, what even is the need of these convolutions? Yeah. Alright, never mind. Okay, so what is the need of these convolutions is that what you're essentially doing is you're introducing a level of filtering. Say you have a complicated image of a cat. Okay, you put it into a neural network. Now it might struggle a bit, it might take some compute power, but here's what I propose. What if instead of putting the input as the figure of the cat, I put the features of the cat? That is, I put the eyes of a cat in one input and the nose of a cat in another input, and the legs of a cat, the tail of a cat in another input. And by doing so, what we're doing is we're helping the neural network in a bit, because we are localizing. The neural network is going to become an expert in localization. Rather than inputting the cat, we are inputting features of the cat. So as you can see, this image is of a square. If I applied the Sobel filter, I got the vertical edges. If I applied the Sobel Y filter, I got the horizontal edges. Now there might exist a complicated filter, right? There are obviously complicated filters which I apply to one image, you get the eyes, right? So this is what the purpose of filters is. So if I have an image of a cat and I apply a certain filter, I get the eyes and the rest of the image will become black, and I feed this into the neural network rather than the entire cat. So this is the intuition behind why we use convolutions. It helps the neural network to learn in a way. Cool. Alright, there's another operation called the pooling operation, or pooling has two things, max pooling and average pooling. First we'll study what the operation does and what is the significance of this. Firstly, alright, max pooling. So we define a pool size or pool length, which is say 2. What we do is, if we have a grid of numbers 29, 15, 0, 100, 28, 184, 70, 30, we choose the maximum value. So the maximum value is 100 here, we choose 100 here, and if maximum value is 184, we choose 100. So we reduce the matrix size. And there's another way called average pooling, is we take the average of these 4 numbers. As it is illustrated by this diagram, you can clearly understand what is happening here. Now, what is the need of pooling? So what benefit does pooling give us? Now, after neural networks, the next architecture was proposed was something like this. Alright, this looks pretty complicated. Stay with me. Remember, this is only from the 1980s. We are not up to 2026. This architecture was there in this was there in 1980s. Yeah. Also, I wanted to mention a thing, but I forgot that. If I'm teaching you atomic structure, I can't teach you Schrodinger's hydrogen atom at the start. Right? You'll have to know Thomson's model, Rutherford's model, Bohr's model, and only with some intuition starts coming into your brain to understand Schrodinger's equation. So this is what we're trying to do here. I can't explain 2026 part directly, how Claude and Gemini work, but yeah, you get the idea. So we're learning basics now. Yeah. So the CNN architecture that was proposed is, you have an input, right? You apply the Sobel filter once, you get horizontal edges. You apply another filter, you get vertical edges. You apply another filter, you get something else. You get a bunch of 10 images, right? 10 feature maps you get. And then what we do is, we pool them together. Now, like I said, pooling compresses it, right? As you can see, this large image becomes this small image correspondingly. So if we had 6 convoluted images, we have 6 pooled images here. I'll explain what pooling does in a while. And then these pooled images, you then put into a neural network for it to learn separately. That, I mean, you can do it parallelly, but you do it. You put them into a neural network so that it learns. Now, what is the use of pooling is, it helps in translation invariance, right? See, you have the digit 7 only, I told you, right? The MNIST handwritten digits. The 7 was in the center in all of them. Now, what if I slightly move the 7 towards the right side? The entire vectors are going to change, right? Because the 7 is moved, they'll have no correspondence at all. So if I put them into a neural network directly, the artificial neural network that we've been studying since the start, the neural network is going to struggle a lot, because the vectors have changed a lot, the input has changed a lot. But what happens when I do pooling is, I take the most prominent features of each half, right? If 29, 0, 15, 100 was there, I'm taking 100, right? So even if I shift the 7 by a little bit, the 100 which was supposed to come there is going to stay there only, irrespective of the translation, because we are choosing the max out of the neighboring items. And also, pooling obviously reduces the size, which is going to help in your computation a lot, because you're literally doing it by 4, I believe. This has 4 into 4, this has 2 into 4, and this is 16. So basically taking the square root, you're doing just reduce it, and that's a good approach. So this is what they do. Input, you detect the important features, and then you pool them, and then you put it into a neural network, and then the neural network learns, and boom, that's much better. So yeah, pooling helps in translational invariance. And now here's one more improvement that Jan LeCun has done in 1998. This was a significant breakthrough which increased the performance of the model. So what he did was that he said that, why should I design this Sobel filter? That why should I write -1, -2, -1, +1, +2, +1? Why should I write it like this? What if I put them with random weights? Like, remember in the start we had random weights, W1, W2, W3. Similarly, he asked the question that, why don't we put them as random numbers at the start, W1, W2, W3, W4? And then, see, what we're doing here is, we convolute it, and then we max pull it, and then we put it in the neural network. So what he asked the question is, why should I design these filters? I'll let the neural network learn through training. So he initializes this as random, and then he tells the neural network to learn it through training. Now this although increases your computational expense, but as you can see here, the error rate drops to 0.95%. Initially it was 3% of your MNIST, what was it? 97.4. Now the error here was approximately 2.5, and then it drastically reduced to 0.5. And this was for only the MNIST part, but if you look at more bigger models, which if you give a cat, it tells it's a cat, a dog, it gives a dog. For these models, it's a significant difference. So let's just have a look at the LANet 5 part, that what the architecture Jan LeCun had proposed, that you have an image, right? The feature maps that we call it are the features generated, the eyes, the hands, the tail, right? You apply those convolutions, you get 6 images, then he pools them, that means he reduces the size and then takes max pooling, and then he applies more convolutions and then he gets these, and then he pools it, and then in the last step he puts it into a neural network. So this architecture has found to be very, very good, and it is much better than your traditional neural network. Firstly, it fixes translation invariance, and through CNNs it is able to localize that your eyes, it is able to localize the things, right? So it fixes the issues with the artificial neural network. And yeah, this is for your basics of computer vision that I wanted to teach you guys. There's one more use of a convolution. What do you think a convolution with equal number does? In the video I should have it here itself. Yeah, what do you think a convolution with all equal numbers does? It is expected to blur the image, right? Let's have a look. Yeah, as you can see, if the convolution has all same numbers, what is eventually going to happen is a pixel is going to get the value of its surrounding pixels average, right? So this gray pixel gets an average of these pixels, and the center image gets it basically gets blurred, as what we call it. So as you can see in this animation, if we pass it throughout, the image is going to get blurred. Yeah, so one pixel is going to get the value of its all the pixels average. Yeah, so average of all these is going to be this. So that's how it works. It happens, and your Mario image, which was fully not fully, but it was good, but now it becomes blurred. Now this is used in encryption, decryption. Sometimes it can be used. Yeah, it has many uses. So convolution networks. So this was the part of it. Alright, as you can see, this image has become completely blurred at the end. Even this image is going to get blurred. Now this has slightly different numbers, but there's also blurring effect. As you can see, it's symmetric. This is known as the Gaussian filter. This is also for blurring approach. Yeah, so that's what the use of a convolution is. Alright, let's start NLP in natural language processing, of how words are used into models in 5 minutes. Alright, my session until now. The normal PC, what models can we run? To what extent? There are some open source models such as Hugging Face. You can get it from Hugging Face. You can see what we do in practice is we don't see our GPUs, no matter how big of an RTX thing you get it, they're still not going to be able to perform very nicely. So there's something called Kaggle, if you guys heard of it. So what we can do there is, if you're a student, you can get up to 30 hours of free GPU time. So there you can, that's what we technically use, right? We use those GPUs on their server, they have it. So they have powerful GPUs, and we import the models and we use it for we use it on their GPUs basically. That's what is usually we do it. Hope that answers your questions. But on our laptop, yes, I thought Kaggle was only for a data set. No, you can it has GPUs, and yeah, it can do that. So yeah, so I hope that answers your question. And alright, let's continue with NLP. So how ChatGPT and all those work. Alright, cool. So the things we're going to be covering here is word-to-vec, word embeddings, and lastly give a brief introduction to RNNs. Alright, so ChatGPT, how does it predict, how does it give an output, right? So what it essentially does is, so if I give an input, something like the cat is sitting on a very simple input to ChatGPT, it goes into the model and it should give an output of mat. That is what we think of a good model is. The cat is sitting on the, our model should output mat or table or some word, right? Now do you get a notion of a function here, that cat is sitting on the is a context of few words that we give as input and the output is a word. So this is again function, so neural networks here as well. So let's continue. From words to numbers, like as I said, machines don't understand pictures. You can't expect a machine. See, by a machine I mean a program like a Python code or a C++ code or a C code. It does not understand pictures, right? So I have to give it numbers. Similarly, what I need to do is I need to convert words to numbers, because the machine can't understand what apple means, right? Because if I have a Python code and I give an input as apple, to be able to perform some math, it has to associate a number with apple. It can't do the math with apple. So we need a systematic way of representing words as numbers. Now the most naive approach would be, you have a vocabulary bit. Let's just see how many words does English have. About 100,000 words are there. Alright, so what you would like to do is give each word a number. Hello 1, hi 2, apple 2, neural 3, network 4, my name 5, and you have 100,000 words like that. So this would be the naive method of what we would get first in our brain, right? But this has some fatal flaws. Let's look into it. Chalo. Right. Let's examine the system of giving each word a corresponding numbers. So let's take two words, hello and hi, which is 45 in our 1 and 45 in our system. As the machine knows, there is no correlation between hi and hello. The difference is too large. So the neural network will have to struggle a lot. Now this is not a bit clear. Let me elaborate a bit more. Alright, let's take two similar words, test and exam. They are usually used in similar contexts, right? So let's say the first sentence is, today's test was extremely. Now you would want to predict hard. So if the first word of the prediction in the first sentence is hard, then the second word should also be hard, right? So today's test was extremely hard, today's exam was extremely hard. But here we encounter an issue. If test and exam don't have similar numbers, that means the numbers aren't close, then the model will have to struggle a lot, because for two different inputs, completely different inputs, you're expecting to get the same output. This is like if you take any one dimension graph, say y equal to x, and you have two different inputs and you expect them to have the same output. This is going to be hard. You have to create a very complicated function, right? The function is not going to be intuitive. So it would be easier if we give test and exam similar numbers, that similar words have similar numbers. Test, exam, awful, horrible, huge, large, these should have similar numbers. Now the issue with this is we can't precisely do it, because English vocabulary is large. I mean, there can exist about 100 synonyms for a word, and then they'll be 100 units separated, but that's not exactly good, because the model will have to struggle a lot. So what we do is, how do we solve this problem? We introduce vectors. What each dimension of a vector represents is a parameter, right? Let's look at an example. Let's say we have three words, cat, tiger and rock, and let's classify them based on two traits, fluffiness and danger. So if you look at cat, it is fluffy and it is less dangerous because people have cats as pets. I mean, it has some danger. I mean, cats can bite. Nick Fury got his eye scratched, so I mean, it has some danger. So I would give cat a fluffiness of 0.9 and danger scale of 0.1, which makes sense. And rock, the tiger, I can give it a fluffiness of 0.9 and danger is going to be 0.9. And the rock as fluffiness of 0 and danger 1, because if I throw you with a rock, you might get hurt. So it has some danger. So this is slightly a better way. We use two parameters of classifying the words. Now are two parameters enough? Now what if I say, how do you classify something else? How do you classify honesty as fluffiness and danger. You can't classify honesty, right? Because it's a feeling. You can't classify it based on your fluffiness and danger. So we need more attributes, that we call it. So what researchers have found is about 300 such attributes would make a good thing, a good representation. Yeah, so according to this example, we can see that tiger and cat are similar in fluffiness and cat and rock are similar in danger. As you can see, these two are similar and cat and rock are similar in danger. So the intuition of word to vectors comes into play, right? So 300 dimensions, as I mentioned, we use about 300 attributes. One would be fluffiness, one would be danger, one would be feeling, emotion, many such attributes we have, and we try to represent these words as vectors. Now again, there should be a systematic way, right? See, I cannot look at them and manually decide for 170,000 words that cat, okay, cat, what is the fluffiness? Okay, let me give it 0.9. Let's look at a lion now. Is it more fluffy? Is it less fluffy? Oh, how do I decide this? So this is kind of an impossible task for me alone to do it. You need an algorithm which decides what words are similar and gives them similar vectors, right? Now this algorithm is CBOW or skipgram, and this is how word2vec was introduced. What word2vec does is it treats the entire Wikipedia and it decides what words are similar, and then it assigns them similar vectors. This was introduced by Google, I think in 2005 or something, and this was a breakthrough in how we represent words as numbers. So there is something I want you guys to look at how these are represented. See, obviously we cannot visualize 300 dimension vectors, right? Because we can only visualize 3D. So what we do is there's something called PCA where we shrink this 300 dimensions into 3 dimensions and try to look at what is happening. All right, let's so all these, by the way, are the words in English, right? And how close a word is to another word depends on its similarity. Let me just take any words that is upper here, and as soon as I click upper, you get the similar words: lower, smaller, higher, sits, northwest, and these are the similar words for upper that that word2vec has found out. If I take any other words such as kills, killing, kill, killed, massacre, injured, destroyed, these are the similar words. I mean, these make sense also, right? Because destroying and kills are usually used in similar contexts in Wikipedia, and this model has learned from Wikipedia. So this is a very good representation. So if we want to give words to a model, what we do is we simply come to this project to word2vec and like, please give me the vector representation of this word, and we take it and we put it to our model. Cool. Now that is sorted, we understood how to represent words as vectors. We understood that part, but the main issue is how do we even create a model, right? Now we understood that we convert words to vectors, but how exactly do we create a model? The model is the main part, right, which makes predictions. So let's look into that now. All right, fine, cool. Let's continue. All right. See, another surprising feature that comes out of this word2vec is this is very famous illustration that you get the two vectors for king minus man plus woman, you get it as queen. I mean, does this make any type of sense that king, you remove the man part and you add the woman part, you get queen? This is a very famous thing that if you see all these vectors and you do king minus man plus woman, you get queen. This is something that has arisen from the word2vec, which is a very cool thing to just for it to be there. I mean, it makes logical sense, right? So that's cool. King minus man plus woman, the vector that we get in this is closely related to queen. All right, let's continue. Now that we have words, we need a model. So what model have we been studying so far? The traditional neural network. So why not just put the context that we have into a neural network and get the prediction? All right, let's look at this slide. What happens in this slide? This morning I took my cat for a. I have given these set of words and I want to predict the next word, which is walk. Alright, so this would have a vector, morning would have a vector, I took my cat, these all would have a vectors, and I would stack them, concatenate them and put it into a put it into my neural network, right? Same thing that we did in the picture. This morning I took my cat, then we make it into a line, and then we put it into a neural network, and we expect it to predict walk. Not exactly predict walk, predict the vector for walk, and then we decrypt it, like this vector is closest to walk, so it must be walk. Right, now the issue with this is the structure of a neural network is rigid. That means how many neurons do I have in my first layer, the input, if you remember from the first slide, x or y. In this slide, this has to be decided by me at the start, right? If I want to change how many input neurons I'll have to go into the code and then completely change the code, because the number of weights will increase or decrease, the number of biases will increase or decrease, the connections increase or decrease. So that here is an issue, as you guys can see, right? So rather than giving this morning I took my cat for a, suppose I input this morning I and I want to predict took, I can't do this. I'll have to go to my code and I have to change my entire code so that it fits for 3 neurons. This is an issue. Now you might say, oh, given 8 words, why should I look at 8 words? Why not I just look for the previous 2 words? Like, what if I just use these 2 words for prediction and keep it as 2? Like, what if I make for a and predict walk? Now the issue with this is the model then can't model long-term dependencies. So if I give an input as France is where I grew up, but now I live in Boston, I speak fluent dash. If this is my context input, I want to predict French, right? But if the model looks at the last 2 words, because our architecture has only 2 neurons in the start, right? Then we are going to predict the answer as English, because English is the most spoken language in the world, and throughout Wikipedia is what we're going to be training. And after speak fluent, you are going to predict English, which is pretty wrong. So now you might say, okay, why not I just increase the context length? I'll just make it as 300 words, right? Now this is also an issue. No matter how much you increase the context size, if I put France in the start and then I put 300 words about something else and ask you what do I speak, then you won't be able to tell France, because you look at the context of only the previous words. So no finite context can, is sufficient for prediction. So this is an issue with ENNs. Now let's look at what this is clearly an issue. So we need a better architecture, like how we had the traditional neural network architecture for image recognition. Then CNNs came, and then we saw how CNNs are actually better than artificial neural networks. So similarly, obviously there are models at ChatGPT, Claude, and they're obviously better than most artificial neural network. But let's look at the next stage of evolution, how we go from Thomson to Bohr, right? So how do humans understand language? If I give you a statement, all right, so humans, they don't remember the entire context, right? They only store the key part. If you read an entire page of NCRT in your 11th and 12th, and I ask you a question about some benzene and some inorganic chemistry, you're obviously not going to go to your brain and then remember, oh, I studied this line, where is benzene? Let me search for benzene, and this is the answer. That's not what you're doing, right? What you're essentially storing is key points, or sometimes you even use mnemonics, right? So that's what humans do. Humans don't read all the words at once and try to make sense of them. We read words sequentially from left to right, one by one, and build meaning as we go on. As we want to keep a running summary in our head of what is happening. This is the main thing that we want to incorporate in our model, is to have a running memory. All right. So things our model should do, right? Handle variable length sequences, which is if I give 8 words as input, or I give 10 words as input, or I give 1 word as input, it should be able to give an output. I don't want to keep changing my code depending on the input length, right? It should also handle long-term dependencies, as I told you, right? It should have a memory that, oh, France, I told it in the starting, then French should come, right? It should maintain information about order. This is also another thing that, see, I told you that if I have words, such as this morning I took my cat for a walk and I just concat and put it there. What if I just shuffle the words? Then will it, this morning cat took my eye. So if I have a word like that, it should handle those sentences as well, right, for representing. If I change the order of the words, it shouldn't, perform bad. That is also another thing that should do. It should share parameters across the sequence. This I'll talk about in a while. So the invention to handle these things, that is to improve the traditional neural networks is the introduction of RNNs, which are known as recurrent neural networks, and let's see how they solve the problem. Yeah, so as I was mentioning earlier, the intuition behind the RNN architecture, how humans process information. Like I told you, if I had given you an entire NCERT page, you remember only the summary of it. So if I give you something like, my name is John and I grew up in France, you tell me this, then in my brain I just remember name John, country France. I don't remember the entire sentence, right? Person John, country France, right? This memory of how much you store is roughly the same size, and it's going to be of much lesser size. If I tell you I like chicken, or I like dessert, and I run, so you just maintain the summary, you just maintain the key points, and this is what we want our model to do. It should not remember the entire context, but it should remember the keywords. So this is where the RNN architecture comes into picture. And holy, what is this? This looks pretty complicated. Oh no, what is this? Alright, so let's just keep this very simple for now. Let's just forget about this diagram, and I want you to focus on a single node, right? A single node here. This is what you call as a single node. So what exactly happens, right? Alright, say I told you my name is. So if I give you my name, you process in your mind, okay, this person is going to tell me his name, and then is, okay, right now he's going to tell me his name. So after every word you tell me, the context keeps on changing. And what does the context change on? It depends on the old information that you had and the new information that you get. So I'd like to introduce some terminology here. Is that so firstly, right, this is a single node that we have here. Okay, x of t is the information that we get at time t. So as I told you, I live in, so if you're at a timestamp 4, France would be the input that we give, not exactly France, the vector of France, because I've explained word to vec, and we get the we use a lookup table to get the vector of France from the word to vec, and then we put it. So yeah, you get France, right? To your model you get input as France, and then you get the context from the previous thing, I live in. So you expect to get a context that is from your previous I live in, and you get a new information France. So using these two informations, what you do is you somehow try to decide what new relevant information you need to keep, right? I live in France. Oh, so I don't need to store the entire sentence. What I need to store is country France, or something like live France. So h of t is known as the hidden state vector. What this vector contains is the relevant information needed for the model for its next steps, and it also makes a prediction of the next word the model thinks it is. Now, this is pretty intuitive to how humans think. We have our context that we have from beforehand, and we get new information, and then we decide what to store, and then we decide what to output as in tell the person. So I live in France, and also I say okay, something like that. So that is the output that we give. So as I said, ht minus 1 is the hidden state of the t minus 1th state. So that is the input that you get. This contains the relevant information up to the t minus 1th instant. So you have told me some context up till there. What I do is I compress everything, and then I store it as the hidden state vector, and x of t is the new information received at time t. And as I said, your h of t, the new information that you want to store, is going to be a function of the new information that you get and the past relevant information that you had. As you can see, relevant information of time t is the function of relevant information up to time t minus 1 and the new information that you get. So this is basically the recurrence relation and how RNNs got their name. And you don't need to get worried about the math and all. You just need to understand the intuition for now, and we can cover the details of the math in another lecture, maybe sometime in the future. But for now, I just want you guys to understand the intuition. So if you look at this complicated diagram again, what happens is it gets in. So don't just forget about these W's and all. So you get information and you get a hidden state. You make a prediction y naught and you pass h. That's what happens. It happens continuously. and after you have given your word, it finally makes a YT cap prediction. So this was about RNNs, and obviously there are going to be faults in RNNs as well. So then came LSTMs. LSTMs are long short memory and long short term memory. So it shows long memory and then short memory. It is also another architecture, and after LSTMs you have a few more architectures, gated, GRUs and all, and after which you finally come into transformers. So your next step of this NLP would be transformers, and transformers are basically state of the art models that we say. ChatGPT is built on a transformer model, and ChatGPT, Claude, Gemini, everything is built on a transformer model. It is the newest model that we have, and it is pretty complicated to understand, but after a few days of practice and even researching more, you feel free to research on YouTube, 3 Blue 1 Brown or whatever you have, and then you can possibly learn transformers. So this would be the end of the session today. You could mark your attendance here. You will receive a certificate from CFI for attending the summer school.